Good morning. My name is Piv Huot. I'm presenting the 2021 HSC Mathematics Extension 2, questions 13, 14, and multiple choice. (13A) indicates locations of all the fourth roots of the complex number a plus ib. Here's a solution to the question Z1, Z2, Z3, and Z4. Bevel response, student realizing the moduli of the roots is greater than 1, but smaller than the original. Calculate the argument of the first fourth roots and use this to determine the argument of the following roots, since the roots are equally spaced about the Argand diagram. Equally spaced the roots about the Argand diagrams. Calculate the argument of each root using the MOV. Common problems. Finding the nth root of a complex number algebraically. Students were not able to transfer the knowledge from solving equations with numerical values to this generalized form of a plus ib. Also, representation of the nth roots of a complex number geometrically. Advice to teachers. Make sure students understand a complex number in polar form and apply the MOV to find the arguments and moduli of the roots of a complex numbers. Use the reference sheet to assist with clarity and precision. Firm knowledge of the MOV, understanding both transformations to the argument and to the modulus separately. Part B. Use an appropriate substitution to evaluate the integral from root 10 to root 13 x cubed times the square root of x squared minus 9 dx. The first method is to use substitution where u is the square root of x squared minus 9. Or alternatively, method number 2 is to let u equals x squared minus 9. Third option is to rearrange x cubed to x squared, then split x squared into x squared minus 9 plus 9, then rearrange the splits, and then integrate and evaluate. The next method is to use trig substitution, where x equals 3 sec theta. It's best if the limit change in terms of arc10. That would make the substitution the easiest. Next option is to change x cubed to x squared x, then use integration by parts. This part was generally well done by the majority of students. Common errors basically with manipulating the integral or limits. Students use various substitutions. With u equals x squared minus 9, or u squared equals x squared minus 9, or x equals 3 sec theta being the most common and most successful. Common problems. Thinking of a suitable substitution before persisting with inappropriate substitution. For example, several students tried to use u equals 3 sine theta or u equals x cubed, and also understanding which trig substitution are suited to which algebraic expressions. Don't forget to find the u limits. This was particularly an issue for students who attempted the substitution x equals 3 sec theta, with several students providing incorrect limits, and some students rounding their limits instead of providing exact values. A number of students appear to struggle with this question, evidenced by multiple attempts made. Advice to teachers. Make sure students use general integration techniques. Clearly show any substitution being used, including any limits of integration, and more accurately produce the new integral. Use trig identities to have a better understanding as to why x equals 3 sine theta or 3 cos theta were poor substitutions. Avoiding unnecessary steps such as converting expression in terms of u back to in terms of x. Avoiding simple errors such as dropping the half in front of the integral sign. Also avoiding simple errors when integrating, particularly when fractional powers are involved. See part 1. Given In is the integral from 1 to e ln x to the power of n dx. Show that In equals e minus n times In minus 1. Here's the solutions. Better response. This part was very well done by the majority of students. Students were able to demonstrate the proof by using integration by parts, by setting u equals ln x to the n and dv as 1. Common problems with this: identify a suitable u, and some students ignore the power of n in the integral. The other problems is differentiating expression using the chain rule. Forgetting to multiply by the derivative ln x was a common error. Advise the teachers. Make sure students using the correct notation, the correct choice for u and u prime, v and v prime when performing integration by parts. Also clearly show the proof step by step. Part 2, this is the volume questions. Students were asked to use part 1 or otherwise show that VA to VB is 1 to 3. Here's the solutions. VA equals pi, the integral from 0 to 1, 1 square minus 1 minus x square dx, which equate to pi on 3. VB equals pi, the integral from 1 to e, 1 square minus ln x all square. When it gets down to here, the I2 is related to part 1. So using part 1 to find I2, and then substitute back to find VB. The option is using the formula. So VA is the volume of the cylinder minus the volume of hemisphere, which gives pi on 3. Whereas VB is the volume of cylinder minus pi, the integral from 1 to e, ln x all square. Then using part 1, use the recurrence to find VB and show the ratio. Better response, write correct expression for VA and VB. Clearly state the volumes required and express these as the difference of volumes. Use volumes of cylinder and sphere to efficiently answer the question. Notice the connection between this question and part 1 in the question, and use the recurrence relationship correctly. Successful students use this to generate an expression for I0, while others found I1 and use integration by parts. Some students use the otherwise methods approach successfully by integrating ln x all square by parts. Common problems. The extension 1 content and volumes of revolution appeared to some many students, and a variety of incorrect expression for VA and VB was submitted. The most common error is many students using v equals pi from a to b y1 minus y2 all square rather than y1 square minus y2 squares. Here's other common problems that VA finding from 0 to 1, which is neglecting the y1 square minus y2 square, again with the VB, and so on. For this part, advise teachers. Make sure students gain a deeper understanding of volumes of solid of revolution by visualizing the volumes of the cylinders and hemispheres that are generated and the limits that are used for these regions. Set out their recurrence formula clearly. Students should set out clearly in a logical order and look to use part 1 when prompted. Generate an expression for I0 rather than finishing at I1, which simplify more easily. And recognizing that it's pi from A to B y1 square minus y2 square for V rather than y1 minus y2 all square. Be careful with the limits. Identify the correct limits of the integration. Visualize and drawing solid of revolution and connecting this to the question. Part D is to do with simple harmonic, given acceleration is -4 times x minus 3. For part 1, the question is between which two values of x is the particle oscillating? The first method is recognizing that acceleration is -4 times x minus 3, leading to v squared equals n squared times a squared minus x minus c all squared, where c is the center of the motion. And substitute the given information when x is 0, v is 8, given an amplitude of 5. Therefore, the particle oscillates between 3 plus 5 and 3 minus 5. Or option 2 is to replace acceleration by d dx half v squared and integrate, find the constant, then equate v equals 0, solve for the extremities. Better response, that's what apply integration techniques to this and finding v squared and then setting v squared equals 0 to find the endpoints. Apply the formula v squared equals n squared a squared minus x minus c all squared and use the given condition to solve for the amplitudes, hence find the endpoints, c plus a and c minus a. The other option is to use the formula x equals a cos nt plus alpha plus c. Then find the derivatives and given the initial condition to solve simultaneous equation to find the amplitude, hence find the endpoints. Common problems, a lot of students assuming the center of the motion was equal to 0. So using v squared equals n squared a squared minus x squared instead of x minus c all squared. The problems is integrate with respect to time rather than using acceleration is v dv dx or d dx a half v squared. Also, students use the formula x equals a cos nt plus alpha plus c, or x equals a sine nt plus alpha plus c, by assuming that alpha is 0. Advise the teachers. Make sure students understand the difference between simple harmonic motion, the center at the origin or not at the origin. Students should be familiar with the ones at the origin with acceleration is negative n squared x, leading to v squared equals n squared a squared minus x squared, or when the acceleration is minus n squared x minus c, leading to v squared equals n squared a squared minus x minus c all squared. Also calculate the extremities of the motion is 3 plus or minus a rather than a plus or minus 3. Also completing the square, students should learn to complete the square on a more complex expression, which are partially factorized or may have a negative at the front of the brackets. Applying acceleration is v dv dx or d dx a half v squared when integrating acceleration in terms of x. Use initial condition to find the integration constant. Understanding the particle oscillate between two endpoints when the velocity is 0. Understanding the relationship between the center of motion and amplitude, that the origin is not always the center. Understanding that if a particle is in simple harmonic motion initially moving, then this initial point is not an extremity. For part 2, find the first value of t when x is 0. Also given the answer corrected to decimal places. The first one is to set the equation x equals a cos nt plus alpha plus c, recognizing the amplitude is 5, n is 2, and the center of motion is 3. When t is 0, x is 5.5, substitute to find alpha. Find the equation, then substitute x equals 0, solve for t. Don't forget that the question is to 2 decimal places. So the answer is t 0.58. Another method is the same as the first one, except this one is in terms of sign. But a student using that the expression in terms of sign needs to be a negative a sine nt plus alpha plus c. Very similar to the previous methods. So a is 5, n is 2, c is 3. So that's give the same results as t is 0.58 2 decimal places. The third method is more difficult if student needs to use v squared in terms of x, find v in terms of x, taking the negative since a particle moved to the left. Then changing v to the x to t. So integrate by putting the limits makes it easier for students not to worry about the constant. Then find that the first time is 0.58 to 2 decimal places. Better response, express the motion in terms of trig in the form of negative a sine nt plus alpha plus c, or cos a cos nt plus alpha plus c with the correct n and c. Also calculate alpha using the initial conditions. Recognizing the particle was initially moved to the left, and thus the expression for the acceleration would be in the form of a negative a sine nt plus alpha plus c, rather than a positive. Represent displacement using a cosine wave. If integrating v in terms of x, recognizing the particle was initially moving to the left, thus the expression of velocity would be negative. Complete the square correctly and integrate the expression using arc sine or arc cos. Common problems. A lot of students forgot alpha or set this to 0 in the equation of x equals a cos nt plus alpha plus c. Particular errors with the amplitude using from part 1 with the incorrect amplitude. Other problems is completing the square to integrate to give the arc sine or arc cos. Finding x in terms of t given velocity in terms of x, including the calculating the constant of integration. Also solving trig equation, particularly when using radian mode rather than degree mode. Some students actually not using the radian modes. The advice to teachers, make sure students understand that a particle under simple harmonic motion is not always centered at the origin. Identifying and using essential information for simple harmonic, center the motion, and n. Apply the formula a equals cos, x equals a cos nt plus alpha plus c, and use the relevant information to find alpha. Then set x equals 0 to find the time. expressing simple harmonic motion trigonometrically and not assuming that alpha equals 0. Considering the direction of motion and effects on the velocity and or displacement equation. Finding displacement in terms of time given velocity in terms of x, including to find the integration constant. Make sure that student can solve trig equations in radian modes. Using acceleration as v dv dx or d dx half v square when integrating in terms of x. Algebraic manipulation before integrating dx to t to obtain the correct answer in terms of in arc sine or arc cos. And also don't forget the integration constant. For question 13, complex numbers, there's 2 marks there, calculus is 9, and mechanics is 4, so the total of 15. Question 14a, evaluate the integral from 0 to pi on 2, 1 over 3 plus 5 cos x dx. Here's a solution using T substitution. So as you can see, this textbook questions, the result is 1 on 4 ln 3. This part was generally well done by most students. Fully simplify fraction before proceeding to partial fractions. Clearly show the substitution of the x, change of limits, and cos x. Take algebraic steps to allow their path to the solution to solve to involve integers. Those that fully simplified the resulting fraction first were most successful. Common problems. There were a number of responses who had problems with factorizing, which give the definite integral in terms of log integration. Common errors are algebraic expression using the T substitutions. The advice to teachers, make sure students simplify algebraic fractions before proceeding, keeping their next steps as straightforward as possible. Factorize using difference of 2 squares accurately, knowing the x to t, and also familiar with the T approach. Part B, this is the force. So B part 1 is to show the resultant force down the slope is 5√3 on 2g minus 2v minus 2v square. Here's a solution. That's the diagram. So the resultant force is 5g cos 30 minus 2v minus 2v square. Because that's the friction force. That's the applied force. This part was very well done by the majority of students. Students who use a diagram seem to be the most successful. Common problems. Many students were unable to correctly resolve forces parallel to the plane and place mg in the incorrect place on their triangle. Advise the teachers, make sure students translating averted problems into a force diagram. Also knowing how to decompose mg parallel to the plane. Be more familiar with the mechanical models of systems involving gravity forces. For part 2, find v when the object's flying down at a constant speed. Correct to 1 decimal place, taking g is 10. is the solution. Just make the force equal 0. Solve using quadratic formula. The one decimal place is 4.2. Better response for this student who used B part 1 correctly identified to have a constant velocity. There's no net force. We're easily able to write a quadratic equation to find the velocity. Keep the quadratic equation as simple as possible. Also correctly apply quadratic equation, identifying which of the two solutions were correct. Correctly answering the question to one decimal place as requested. Common problems. Many students did not solve the quadratic equation properly to find the correct response. The other problems issue with student is either they're not rounding to one decimal place or choosing the negative because it was going down. A few students did not even attempt to integrate. Actually, a few students tried to integrate with respect to t. Advise the teachers. Make sure student reading the question to respond to the appropriate number of decimal places in the question. Solve a quadratic equation. Understanding which direction is positive and negative, and making an appropriate selection. Be more familiar with mechanical models of systems involving gravity forces. See part 1. This is a textbook question. Using the morph and binomial expansions to show cos phi theta equals 16 cos theta phi theta minus 20 cos cube theta plus 5 cos theta. So expand cos theta plus I sine theta to 5 using the morph, also using binomial, and equating the real parts. The option is to use a compound angle formula. Better response, student actually state the binomial expansion in the morph separately. Write the most generic form of the binomial expansion, and not to work with that algebraically until equating the real parts. Introducing algebraic errors into the expansion. Clearly writing the binomial expansion with its numerous powers and operators correctly. Connect their real components of both to actually successfully finalize the question. Common problems is the algebraic mistakes with the expansion and not being careful with their powers were the common mistakes. Students use alternate methods such as expanding factor by factor or using additions of angles properties were less successful. Advise the teachers. Make sure students being accurate with writing down the powers correctly. Taking care with basic numbers and algebraic skills when expanding a complex binomial expansion when it involves powers and negatives. For part 2, by using part 1 or otherwise, show the real part of e to the I pi on 10 equals the square root of 5 plus root 5 all over 8. The first method is student recognize the real part of e I to the I pi on 10 is cos pi on 10. Substitute pi on 10 into part 1. Then realizing solving a quadratic equation using quadratic formula to get cos pi on 10. Also recognizing that cos 5 theta equals 0, finding all the 5 roots of the trig equation. The best thing is to actually use the cos graph to see that cos pi on 10 is the largest of this. Therefore, cos pi on 10 is the square root of 5 plus root 5 all over 8. Another method is actually to solve the fifth root of unity and then find the sum of one roots at a time, then solving the quadratic equations. Also recognizing that this is cos pi on 5. Use a double angle formula for cos, then they can find cos pi on 10. Another method is actually very similar. Again, find the fifth root of unity. Also factorizing z to the 5 minus 1. And then equating the real part of z. Again, solving the quadratic formula in terms of cos pi on 5. Also use a double angle to establish cos pi on 10. The other option, again, you can see that factorizing this and solving reducible to quadratic formula, getting cos. In this case here, we can actually see that with the sums of roots, so we've got cos pi on 5. Again, use a double angle formula for cos. You get cos pi on 10. The next one is very similar to the previous methods. As you can see, again, we're solving this, but this time, what we actually want to do is to equating the imaginary parts instead of the real parts. So equating the imaginary parts, we're getting sine 2 pi on 5. Then sine 2 pi on 5 is cos pi on 10. So that's give us the result. Better response actually applying C part 1 to form a quadratic equation that could be solved by factorizing and the quadratic equation using substitution. Form a polynomials by solving cos 5 theta equals 0 and determining its distinct roots. Identify that cos pi on 10 is not equals to 0 and therefore a root of a quartic. Decide that the result is either cos pi on 10 or cos 3 pi on 10. Compare the values of cos pi on 10 to cos 3 pi on 10 using either a graph and or stating its decreasing function in the appropriate domain and deciding that it's the greater of the two. Common problems is students taking cos square pi on 10 equals 5 plus root 5 on 8 because they believe that cos pi 5 plus root 5 on 8 is positive, whereas 5 minus root 5 on 8 is negative. Students actually engage with this question by guessing the value of theta should be, but all they're doing is just guessing. Many actually guess the angle to be pi on 50 because of the 5 theta leading to pi on 10. Students usually guess these values because of the starting values and finding the solution to cos 5 theta equals 0. This resulted in students not having appropriate roots to compare when making the final argument, the choice between plus or minus. The advice for teachers, make sure the student find the roots of the polynomials from C part 1, which is solving cos 5 theta equals 0. Compare cos pi on 10 to a root, not an arbitrary value. Correctly justify that cos pi on 10 is the square root of 5 plus root 5 all over 8. Through the use of a correct comparison, or demonstrating the cosine function is decreasing over the domain from 0 to pi on 2. Here's the breakdown of question 14. It's 4 marks on calculus, 4 on mechanics, and 6 on complex. The total is 14. This is the start of the multiple choice. Question 1. Which of the following vectors is equal to AB plus CQ? The most common response is B, then follows by D, then A, then C. And the correct response is B. Question 2. Which expression is equal to the integral of x to the 5 e to the 7x dx? The most common response is A, then C, then B, and the list is D. And the correct one is A. Question 3. Which of the following is a vector equation of the line joining the points A and B? The most common response is B, then A, then C, and the least common response is D, and the correct answer is B. Question 4. Consider the statement. Which of the following is the contrapositive of the statement? The most common response is C, then B, then D, and the least common response is A. And again, the most common response is C, and the correct answer is C. Question 5. Which of the following statement is false? The most common response is D, then B, then C, and the list is A. And the correct answer again is the most common response, which is D. Question 6. Which polynomials could have 2 plus I as a 0, given that K is a real number? The most common response is A, then D, then B, and then follows by C. And the correct answer is A. Question 7. Which diagram best shows the curve described by position vector between 0 and 4 pi? The most common response is D, then C, then B, and the least one's A, and the correct answer is D. Question 8. The speed of the particle is increasing. Which of the following diagrams shows an acceleration which would allow the particle to follow the curve to B? The most common response is D, then C, then A, and the least one is B. And the correct answer is D. Number 9. Sam wants to check if the statement is true by turning over the minimum number of cards. Which cards should Sam turn over? The most common response is B, then A, then D, and then C. And the correct answer is B. Question 10. Consider 2 non-zero complex numbers Z and W as vectors. Which of the following expression is projection of Z onto W? The most common response is A, then C, then D, and the least common response is B. But the correct answer this time is the second most common response, which is C. Here's a breakdown of multiple choice. Vectors, calculus, vectors, proof, complex numbers, vectors, mechanics, proof, and complex. In the whole paper, 17% on proof, 20 on vectors, complex numbers 23, calculus 20, and mechanics 20. So it's a very well spread out papers. That concludes the multiple choice questions. Thank you.